Today we shall discuss about energy. We already know that energy is the capacity or the ability to do work. A body capable of doing some work is said to possess energy, and it is measured by the amount of work that the body can perform. Whenever a body does some amount of work, its energy decreases, and when its work is done on the body, its energy increases. So we can say that work is done at the expense of some amount of energy. So whenever we measure energy, we do so in terms of the work that the body can perform. So there is always a transfer of energy whenever work is done, and thus we can say that energy and work are equivalent. Energy is of different forms. At present, we shall discuss about mechanical energy, and we know that mechanical energy is either kinetic or potential. Mechanical energy is the energy that the body will possess by virtue of its state of rest or by virtue of its state of motion. So energy possessed due to rest or motion, due to the state of rest or the state of motion, is mechanical energy. So if mechanical energy is kinetic, then it is the energy possessed by virtue of motion, and if the mechanical energy is potential, then it is the energy possessed by virtue of remaining at rest. Now, not only the body is at rest, it might be at rest in a very deformed state, it might be in rest at a relaxed state, or it might be at rest due to some configuration. So, potential energy precisely is not only due to the state of rest only, it is also due to the state of configuration of the body. The body is either in a deformed state or in a relaxed state or whatever. Say for example, an elastic string or a stretched string, a stretched bow, a spring in either compressed condition or in elongated condition, it will always possess some amount of potential energy by virtue of its configuration or its state of deformation. And kinetic energy is simply due to the state of the motion of the body. The body is definitely moving, and that's why it has some amount of kinetic energy. If the body is at rest, its kinetic energy is definitely zero. But at rest, the body will possess some amount of potential energy. So let us try to find an expression for the kinetic energy acquired by a body. Suppose a body of mass m, which is initially moving with a velocity v, has been brought to rest by some force that retards its motion, and let A be the retardation produced by the same force, and the body prior to coming at rest has travelled a distance s. So, as we have already discussed the equivalence between work and energy, we can say that kinetic energy acquired by the body is the work done by the retarding force in stopping it. So definitely the body was having some velocity v, a retarding force F acted on it, it produced a retardation A, the body came to rest, and before coming to rest it has travelled a distance s. So now we can say that the kinetic energy is the product of force and displacement, because we know that work is the product of force and displacement. In this case, the force is exactly along the same direction as that of the displacement. So here the value of cos theta is 1, so we are just writing k is F into s. We already know by Newton's second law of motion that force is the product of mass into acceleration. We already know the equation v square minus m square is 2as, that relates the initial velocity, the final velocity, the retardation or the acceleration, and the displacement of the body. In this case, the initial velocity u is actually v, because we have already assumed that the body was moving with the velocity v. So the initial velocity is v here. Because the body has come to rest, the final velocity v is 0. And because the force has produced a retardation, we should write, instead of a, minus a. So this equation now becomes 0 square minus v square is twice of minus a into s. That implies v square equal to 2as, and so s equal to v square upon 2a. Now let us substitute this value of s in this equation. Instead of force, we are writing mass into acceleration, and instead of s, we are writing v square by 2a. So you see that this a cancels out, and what we get is m by 2 into v square, which means it is half mv square. So kinetic energy is half into mass into square of the velocity of the body. So this is an expression for kinetic energy acquired by a body. Now we can relate the kinetic energy with the linear momentum of a body. The linear momentum of a body, which is denoted by the symbol p, is the product of the mass and the velocity. So from here we can write v equal to p by m. Substituting this value of v in the equation of kinetic energy, what we get is k equal to half m into p by m whole square. Because v is p by m, so this is p by m whole square. V square is becoming p by m whole square. So this is p square by 2m, because in the denominator you get m square, and in the numerator there is m, which will cancel out and produce a single m in the denominator. So this means k is p square by 2m. So if you cross multiply, you will get p square as 2mk. P square as 2mk. If you take the square root, you will get p equal to root over 2mk.